Warut. Thanks for coming. Warut will be giving today's algorithm seminar talk. He's a CS theory student at Stanford. He has worked in algorithms, mechanism design, fair division, his general area of algorithm engine theory. Today we will hear about simple pricing schemes for the cloud.
Okay. All right, so first of all, I would like to thank Costas for inviting me to give this talk here, and obviously thanks to all of you for being here. So this is joint work with Ian Cash and Peter Key, both from Microsoft Research, and I just presented this work last month at the Wine Conference in Bangalore, India. So I probably don't need to convince you of the importance of the cloud. Right. So there's a huge amount of computation occurring there with billions of dollars involved. And so it is crucial to come up with a good pricing scheme. And here the central question is how do we decide which jobs to accept from the set of incoming jobs and what prices should we charge for these jobs? Or in other words, what makes a good pricing scheme? And here I'm going to focus on two things. So first, we want the scheme to have strong welfare and revenue guarantees for obvious reasons. But in addition to that, we also want the scheme to be simple. So we want it to have to be easy to implement and also easy to participate in. What we do in this work is that we combine the two objectives and show that we can more or less have the best of both worlds. So there's this simple pricing schemes that can perform almost as well as more complex ones with respect to welfare and revenue guarantees. And to make things a little more concrete, let's take a look at the pricing scheme that's used for virtual machines on Microsoft Azure. So here, once the user specifies some basic parameters such as region, type, and instance size, the price is then calculated just by multiplying an hourly based price by the number of hours that you want and the number of virtual machines that you want. So for example, in this case, the hourly based price is $0.153 per hour. We want one virtual machine and we want it for 100 hours. And so the final price is just $15.3. So you can see that this is a very simple pricing scheme, very easy to understand. On the other hand, you can imagine a more involved pricing scheme where for each number of hours that you might want, there is a specific price for that number of hours. So the question that we study in this work can be phrased in this setting as follows. How much more welfare or revenue could be created if instead of this simple multiplication formula, we were to use a complex table that specifies the price for each number of hours? And what we show for this setting is that, in fact, the simple multiplication formula already gives you at least a 50% approximation compared to the complex table, both in terms of welfare and revenue. And so that's for the setting with a single server. We also extended our results to multiple servers. So here you could imagine that the servers may be located in different parts of the world, so they can be receive different kinds of jobs. And what we show is that setting a single price for this group of servers, even though they receive different kinds of jobs, can provide a reasonable welfare and revenue approximation compared to setting different prices for different servers. All right, so before going on to the details of our results, let me mention some related work. So there's been a lot of recent work on designing good scheduling mechanisms with welfare guarantees and incentive properties. I just want to highlight a couple of them. So Azure et al. Showed that we can get a constant approximation of the optimal welfare with a truthful mechanism, but only if slackness is allowed. So that means their mechanism might not tell you immediately whether your job is accepted or not, so it delays commitment. And also it could preempt your job. So your job could be preempted and then resumed later. And later, Begani et al. so that we can still get a constant approximation of the welfare even without slackness, but only if you have information, so the stochastic information on the jobs. And in both of these works, as well as several others, prices depend in a complex way on a number of parameters, typically including job length, arrival time, deadline, and value, as well as on the current state of the system. And in practice, this information is not always so easy to obtain. And even when it's possible for the participants to figure out this information, there's often a cost, both in terms of time and resources, to figure it out. So in this work, we show that good results, so good guarantees, are possible with no upfront information. And our work falls into a broader area of the design and analysis of simple mechanisms, in particular posted price mechanisms, which also has a very rich and beautiful literature. All right, so let's get into our model. So we start with a single server. Each time step, a job of some length is drawn with some probability. And the value for time step of the job is drawn from some distribution that is independent of the job length. So later on, we'll actually relax this assumption. And we're allowed to set a price per time step. So if the value of the incoming job is at least this price, then the job is accepted, and then the machine executes this job for however many time steps it takes. Otherwise, the job is rejected. So the question that we ask is, when we set this price, do we need to take into account the length of the job? So can we just set a single price per time step for any job length, or should we discriminate between job lengths? And note that if we're allowed to discriminate between job lengths, then what we want to do is that we would want to set a higher price for longer jobs as a premium for accepting it for a longer amount of time. In other words, once we accept a longer job, we're stuck with it for a long time, and so we should set a higher standard for accepting it. So as an example, Amazon recently started offering a product called defined duration spot instances, where users are allowed to specify the number of hours in hourly increment from 1 to 6 hours. And unlike the usual spot instances, where the prices can fluctuate periodically depending on demand and supply, here there are already prices fixed beforehand. And the defined duration prices are higher than the usual spot prices, but still lower than the on-demand prices. As you can see here, the price per hour indeed goes up as the number of hours increases. So here, for example, in the first row, we go from 0.15 to $0.142 per hour for 1 hour to $0.157 per hour for 6 hours.
Question. Does this assumption that you want to charge more for longer jobs, is that because there's more jobs than capacity?
Right, but also, so that's part of it, and also because there's preemption, right? So it could be that, for example, for spot instances, if the spot price goes above the price that you set, then your job could be preempted. Okay. And so here you're paying the price for the guarantee of having your job executed.
Okay.
Yeah.
Question.
Yeah.
So just kind of following up, I had similar kind of question. So coming back to the model, right? So you have one job coming in every time step.
Right.
Now, whether I choose a long job right now or a short job, or rather, what's the cost in picking a longer job? Whether I choose a job for 2 time steps, I'm making the money anyway for 2 steps.
Mm-hmm.
And then things will just proceed from the 3rd step onwards.
Right, but then in between, you're missing the chance of choosing other jobs, right, which could have a higher value. So it's like once you're making the commitment of executing this job for that amount of time.
Right, there could be a higher value.
Exactly.
So in here, does the user need to know the length up front, or can it just run a job however it finishes and then they get charged?
Yeah, so actually here we assume that the user knows the length upfront and then submits that to the mechanism.
So the metric is revenue or efficiency?
Yeah, it's actually both. So both welfare and revenue work for the approximation that we're going to give you.
So one question related along the same line. So is there ever a time that you would want the cost for a longer job to be less per hour? Because in some sense, the job is also kind of committing to being served for 6 hours. So it's kind of nice to be able to serve this high value job for 6 hours.
Yeah, so there could be that effect, but I think that's outweighed by the ability, by the guarantee of having the job executed for that number of hours. And I mean, indeed, both in our model, in our model, the analysis of our model, and also in practice for this Amazon's defined duration spot instances, turns out that ultimately what you want to do is you want to set a higher price per time step for longer jobs.
I guess my question is, theoretically, is there a case in which it is lower, but in practice there is not, or even in theory, there is no such instance in which you would want cheaper, the long jobs to be cheaper?
No, so in theory, so if you solve the model, then you would find that indeed, like in all instances, you always want to set a higher price for longer jobs. Yes.
Okay, thanks.
Any other questions? Okay, cool. So let me move on. All right, so as I mentioned earlier, our main result in this single server setting is that setting the same price per time step for all job lengths can get you at least 50% of either the welfare or revenue. So this metric depends on what you want. And this welfare or revenue that can be obtained by setting an individual price for each job length. And in fact, we can say something even stronger than that. So what we can say is that this single price can be chosen from one of the discriminatory prices. What that means is that, so suppose you have the optimal set of prices in the multi-price setting, then the optimal price in the single price setting, well, it could be different from any of those prices, but what we can guarantee is that choosing at least one of those prices as the single price will get you this 50% approximation. So you don't need to fetch the single price from out of nowhere. You can get it exactly from this set of prices. And this approximation also holds for arbitrary, so not necessarily optimal discriminatory prices. So you just start with any set of prices in the multi-price setting, then still it's true that using one of those prices in the single price setting will get you this 50% approximation. We don't make any assumption on the distribution, so it could be a discrete, it could be continuous, could even be a mixture of the two. And this bound is tight, even when there are only two job lengths, if the two job lengths are far apart. So if one is 1 and the other goes to infinity. And one important thing to keep in mind is that, this 50%, it might not seem that impressive because you're losing half of your welfare or revenue, but this is a worst case bound. And so in practice, when the input is not adversarially tailored, we can expect to do quite a lot better than this guarantee. Okay, so recall that this 50% is a worst case bound over a number of parameters, right? Over the set of job lengths, the distribution over job lengths, and the distribution over job values. Another feature of our result is that when there are only two job lengths, or more generally, when we know more information on the parameters, we can actually get better approximations. And in particular, when there are only two job lengths, we can even get a tight bound on the approximation if we know the job lengths and the distribution over them. So, for example, if the job lengths are 1 and 2 and they occur with equal probability, then this bound goes up to about 86%. And that is tight for bimodal distribution, where the value is either low with high probability or high with low probability. So this is the graph for the distribution. So here on the x-axis, we have job value, and on the y-axis, we have probability. So we have on the left-hand side, low value with high probability, and on the right-hand side, high value with low probability.
Good question. Just so I understand the setup. So we're basically at each time one job comes in, I have to decide. So if it's a job of length 2, I have to, if I don't accept it, that means I don't get anything for one time.
That's right. Yes.
Okay.
Yes. Mm-hmm. Yeah, and right. So intuitively, what we want to do here is we want to accept all short jobs, but only long jobs with high value, and that is only possible if we can discriminate between job lengths. Okay, so right. So that was the overview of our main result in the single server setting. Now let me go into some more detail what method we used to obtain this result. And I'm going to do that with an example, a simple example, which I mentioned earlier, which is we have only 2 job lengths, 1 and 2, and they occur with equal probability. And as I mentioned, in this case, we get the guarantee we get is about 86%, or to be more precise, it's 6/7. And so what we do to get this guarantee is that, well, first of all, so we write down the formula for either the welfare or the revenue of each setting, so of the single price setting and of the multi-price setting. So for example, here we're doing the welfare, and if we set the prices P1 and P2, then we can write the formula for the expected welfare per time step as a formula right here. So it's in terms of the integral from P1 or P2 to 1 and of x times fs. So that's in some sense that's like the expected value of an incoming job, provided that the value is above the price P. I mean, so it's not exactly that, because for the expected value you have to divide by the probability that the job is accepted, but it's certainly something related. And then in the denominator, we have the term capital F of P2. So that's the probability that the value of an incoming job is below P2, or in other words, the probability that the job is rejected. So yeah, in this case, actually, when one of the job lengths is 1, you can see that it's always optimal to set the price for that job length to be 0, because the job of length 1, right, it doesn't interfere with future jobs, so you should always accept it. But we won't even need this fact in order to show our guarantees. So because remember, our guarantee holds for any set of prices in the multi-price setting. And okay, so now that we have the formulas, so what next is well, probably the first thing you want to do is that you write down the inequality that you want to prove. So what we want to prove? So we want to show that you can get an approximation of the welfare in the multi-price setting by setting one of the prices as the single price. So that's in the inequality, the first inequality here. So the
I have a question.
Yes.
So the value of a job, is it when it's drawn, is it the value per time step, or is it the value of the whole job?
It's the value per time step, yeah. So there's a single distribution, that's the value per time step, and then this distribution is for jobs of any length.
Okay, thanks.
I have a question. So in these formula, you somehow don't expect the formula to be much more complicated, where you have to incorporate all the interference that happens if you take a long job, and then the next time step is kind of held up. So if I take a job of length 2, then the next time step is kind of the value is correlated with the previous time step.
So there's no right. So I guess for any job, the price per time step. So there's only one price per time step for that job. So it's not going to be like it's not like after one time step you redraw this value per time step. Yeah. So if the job of length 2 arrives and it has the value per time step 0.4, then that holds for both time steps.
Right. And the formula doesn't explicitly have to say that because of linearity of expectation or something.
Right. So actually, so you can write down. You can actually. It's not very complicated to write down this formula. So you have the quantity you want to solve for is the expected welfare per time step, and here you can imagine a very long time horizon, and then so for example, say you have jobs of length 1 and 2, you can think of okay, job of length 1 comes in, it has we set this price P1, and what's the probability that it's accepted. If it's accepted, how many time steps it takes, what's the welfare that it yields, and so on, and you can solve for this formula.
It turns out to be this formula.
It turns out to be this formula. Just okay, yeah. So right. So in the claim is the inequality that we want to prove, and then in symbol, so that just follows from the formulas in the previous slide. So this is the inequality that we want to prove, and even though it might seem a bit complicated, it's actually in terms of just 3 main quantities. So first is the ratio between the 2 integrals, and then we have capital F of P1 and capital F of P2. And so we're going to divide into 2 cases here, which is, I think, very natural here. So the first case, we have this integral from P2 to 1 is relatively large compared to this the integral from P1 to 1. So intuitively, what that means is that the value of the job, value of a job when it has value above P2 is relatively large compared to value of the job when it's above P1. So there's a lot of value from jobs of value above P2. So what we're going to do there is we're going to set a single price P2. And in this case, we take the second term in the math here, and you can see that the denominators cancel, and so we're just left with comparing the numerators, and that's in terms of the 2 integrals, and then the inequality is just followed that from the case assumption of case 1. And then for the other case, so now the value of jobs above P2 is relatively low compared to those above P1. And so in that case, we just set the single price P1. So we have the first term in the maps. And so now the denominators no longer cancel. So we have 3 minus capital FP2 on the left-hand side, and 3 minus capital FP1 on the right-hand side. But what we can do there is that we just assume the worst case on the denominators. So we assume that f of P1 is 0 and f of P2 is 1. So this is the worst thing that can happen for this inequality. And even in this worst case, it turns out that the inequality is still going to hold. And that's also why the inequality is tight for a bimodal distribution. Right? So we want one price to accept pretty much all jobs, and then the other price to accept pretty much no job.
But the mix between short and long jobs doesn't occur in this math. It doesn't appear.
The mix between
what's the fraction of small jobs versus large fraction of small jobs and fraction of large jobs? Is that here on this slide? Just to be clear that
So right. So this is going to be go to very close to 1, and this goes to so this is very close to 0. But then the quantities that going to matter is that the ratio between the welfare that you get from short jobs and from long jobs. So that will be held at some constant. So because the fraction of short and long jobs is going to be, I mean, we're going to have pretty much all jobs being short jobs in this distribution, but then the long jobs are going to have give you much more welfare. So the value per time step of the short job is going to be very close to 0.
So in this distribution, reds are also short jobs.
Right.
They're low value short jobs, and the greens are high value long jobs.
Exactly.
Oh, okay.
Yeah. And yeah. So right. So that's basically the proof for this illustrating example. And in the general case, so we could have any 2 job lengths like A and B, and any distribution over the job length, and the proof just follows. It's more complicated, but the idea is more or less the same. Okay, so any other questions up to this point?
So it's reminding the value per time step was independent of the job length in the
Right,
distribution?
so far, yes, we've been using that assumption. Yes. Okay. So so let's take a look at so that's only for one example with jobs of length 1 and 2. So let's take a look at what this approximation ratio looks like for more general cases. So if we have jobs of length 1 and arbitrary b and still occurring with 50-50 probability, then we get an approximation ratio that's about 2/3, and it goes to 2/3 as b goes to infinity. So it decreases and approaches 2/3. And it makes sense that it decreases because as the other job length gets longer and longer, there's more and more to be gained by being able to discriminate between job lengths. And so this ratio should go down. And then if you have job lengths 1 and b occurring with arbitrary probabilities r and 1 minus r, then we get the approximation ratio, and it's always at least a half, and approaches 1/2 when b goes to infinity, and then r goes to 1. So the longer job lengths get very, very long, and then almost all probability is put on the shorter job length. And finally, in the most general case with two job lengths, we have jobs of length a and b occurring with probability r and 1 minus r. So we still get some formula which is tight for these job lengths and these probabilities. And it's always at least 1/2. To recall that this 1/2 holds even for any number of job lengths. But it's tight even for a pretty particular case which is two job lengths 1 and b occurring with r and 1 minus r and with the appropriate conversions. All right. So so far we've been comparing the single price setting to the multi-price setting, right? So in an extension, we show that we can actually compare the welfare from setting a single price to an even higher bar, which is the offline optimal welfare. So here you can imagine that this is the welfare that you get when you see all the realizations of the job lengths, job values, and everything, and then you can schedule all the jobs in such a way as to maximize your welfare. And what we show is that still in this case, there exists a single price that can get you 50% of the offline optimal welfare. And here also, we don't need the independence between job length and value per time step. However, there are also some disadvantages to this method compared to the method that I just described to you. So for this result, this single price cannot be fetched just from a small set of prices, and also it does not yield a bound for non-optimal prices. And even if you have more information on some parameters, it's not going to get you anything more than this 50%. The proof of this method uses techniques from the profit inequality literature, which I'm going to describe to you next.
A question?
Yeah.
So even in this offline case, is it still when a job comes, I still have to either accept it or reject? I can't delay it till later. Right.
Because so this is a pricing scheme. So you set a single price, and then if the job is at least this price, you accept it. If not, you reject. So this is a kind of simple scheme, right? Okay. So how do we show this result? So let's assume that there are jobs of classes 1 through n. So here we're going to assume a discrete distribution. The result also holds even if we have a continuous distribution. We can just replace all sums by integrals. But for simplicity, let me just show it for a discrete distribution. So we have jobs of these classes, and job class J arrives with probability Rj, hash length Aj, and value per time step Vj. And these values can be, some of these values can be the same across different job classes. So remember, we're not assuming independence between job length and value per time step. And what we can do is we can write an expected linear program to upper bound the maximum welfare per time step. So here opt is the maximum expected welfare per time step. And this quantity, so this the ratio of Xj over Rj, you can think of as the probability of that if a job of type J, a job class J arrives, what's the probability that it's accepted given that it's arrived, right? So a job of class J arrives Rj over time, and it's going to be accepted Xj over Rj of the time given that it arrives. And so in total, it's going to be accepted Xj of the time. And of course, this Xj cannot exceed Rj. And then, so a job of class J arrives, so a job of class J is accepted Xj of the time. And whenever it's accepted, it's executed for Aj time steps. And so this last constraint here just says that we cannot accept more jobs than would saturate the machine if when all these jobs are executed. And finally, this opt, so it's just the maximum of this. So the welfare can be calculated by the sum over all job classes of the time, the percentage of the time that the job class J is accepted, times the value per time step of that job class, and then times the length of that job class. And so that's why we have this linear program. And so how does this linear program help us get our result? So what we do is we set the price P to be opt over 2. So this might seem surprising, but it's actually a standard technique from the profit inequality literature. And we let Yt be the probability that the server is occupied at time t. And so that it might be occupied because of the job that just arrived at time t is accepted, or it could be a job that arrived at some earlier time, but it's still being executed at time t. Now, what's the expected revenue at time t? So that's just the price times the probability that the server is occupied at time t. So that's Yt. And the price we just set to be opt over 2. And what about the surplus, expected surplus at time t, right? So here I claim that it's at least this quantity here. Why is it? Well, so the probability that the server is not occupied at time t, so that's 1 minus Yt. And then, so we have this probability times the expected surplus from the incoming job at time t, right? Because so this probability we're already conditioning. So this is the condition that the server is not occupied at time t, and then so we know that we can accept the job that arrives at time t. So we look at what's the expected surplus from that job. Well, so it's just the so Rt, remember, is the probability that so Rj is the probability that the job of class J arrives, and then if it arrives, so what we get is the difference between the value of the job and the price, and then once it's accepted, we have that job for whatever time steps that it's executed. We have this quantity on the left-hand side. And then to go from the left-hand side to the right-hand side, so 1 minus Yt goes straight over. And so remember from this slide that Rj is at least Xj, right? So if we replace Rj by Xj, and then we have the term Xj times Bj times Aj, that's exactly opt right here. And then the other term, we have a minus P times Rj times Aj. So Rj has been replaced by Xj, so we have Xj times Aj. And that's exactly this quantity here, which is at most 1. So that's a minus sign. We have, so this Rj times Aj is at least 1. And then we're just left with a minus P. But P is, we set it to be opt over 2. So we have a minus opt over 2 here. So what it ends up being is opt minus opt over 2, which is just the opt over 2 right here. So that's why we get the term on the right-hand side. And finally, so the expected welfare. So welfare is just the sum of the revenue and the surplus, right? And then we use linearity of expectation, and so we just sum up the two quantities, and what we get is exactly this op over 2, which is half of the offline optimal welfare. And yeah, that's the proof of this result. So any questions about that?
So I guess one thing which is confusing me
Yeah.
is in the math. So expected revenue at T and expected surplus at T are presumably the surplus at time step T. That's what it is, right?
Right.
But then the formula for surplus has the AJ in it, which is the length.
Yeah. So I guess we calculate them in slightly different ways. So you're right. So for revenue, so we actually look at the revenue at time T, so of the job that's executed at that time step. But then for the surplus, we calculate the surplus when for jobs that is accepted at time T, but then we calculate it for whatever time step it takes to complete that job. So we're not going to calculate it in between, in the middle of the job. So it's right that we calculate in different ways, but that's fine.
In that case, the expected revenue at T should have a greater than equal to?
Revenue.
Because the YT, never mind, I'll take it offline.
Yeah, sure. Okay, so yeah, so that was for one servers. So as I mentioned earlier, we also extended our results to multiple servers, and I'm gonna just mention that briefly. So here we still assume that each time step for each server, a job of some length pairs with some probability. And right, so the set of job lengths and the distribution over job lengths can be different for different servers. So for example, that could be because the servers are in various geographic locations, or they're used by different users. The question that we ask here is analogous to the one that we asked before, except that here we are allowed to, we have 2 dimensions in which we can discriminate. So we can discriminate between job lengths, but also we can discriminate between servers. So the question is, can we do well by setting the same price per time step for all servers and all job lengths, compared to setting an individual price for each job length and each server? And the answer is, again, positive. So what we show is that for any prices we set in the multi-price setting, we can achieve an approximation that is so it's logarithmic in either the number of servers or the maximum job length. So what this means is in most situations, as long as the parameters are not too extreme, we're not going to lose too much welfare or revenue by setting a single price for all job lengths and all servers. And as before, if we have more information on some of the parameters, or we put some more constraints, like for example, if we can still discriminate between servers, but we have to set the same price for all job lengths of each server, then we can again obtain a better approximation.
Is the value distribution common?
Here, yes. So across servers, no. So across servers, we can have different value distributions.
Oh, okay.
Yeah, but in each server, we have the same. Yeah. Right. So this corresponds to the servers being in different geographic locations. So you could think of the servers as being separate from each other. So one could be in Europe, one in Asia, one in North America, and they just receive different kinds of jobs, so different distributions of job length, of job value. Okay, so yeah, so let me conclude. So in this work, we study how well simple pricing schemes that do not take into account certain parameters can approximate more complex schemes with respect to welfare and revenue. And our results help explain why such schemes are efficient in practice, including the scheme for Microsoft Azure that I showed you earlier. And since simple schemes do not require agents to spend time and resources to determine their specific parameter values, our results also serve as an argument in favor of using these schemes in practice. And finally, again, an important thing to keep in mind is that all of our results are of worst-case nature, And so if you actually implement these schemes in practice, the guarantees on welfare and revenue is likely going to be quite a lot better. And that's all for me. Thank you.